Welcome to this problem walkthrough. In this session, we'll tackle LeetCode problem number 1888, titled Minimum Number of Flips to Make the Binary String Alternating. This problem challenges us to transform a binary string into an alternating pattern with the fewest number of flips. It's an exciting problem that tests our understanding of string manipulation and optimization techniques. Let's dive in and solve it step by step. The problem asks us to work with a binary string, which is a string consisting only of zeros and ones. This binary string is considered alternating if no two adjacent characters are the same. For example, strings like 0101 or 1010 are alternating because each character alternates between 0 and 1. On the other hand, strings like 1110 or 0001 are not alternating because they contain consecutive characters that are the same. To solve this problem, we are allowed to perform an operation where we flip any character in the string. Flipping means changing a 0 to a 1, or a 1 to a 0. The goal is to determine the minimum number of such flips required to convert the given binary string into an alternating string. Additionally, since the string is circular, the first and last characters are treated as adjacent, so the solution must account for that as well. The input to the problem is a single binary string, and the output is an integer representing the minimum number of flips needed to achieve an alternating string. Let's look at some examples to better understand the problem. In the first example, the input string is 111,000. To make this string alternating, we can flip the fourth and sixth characters. After these flips, the string becomes 101,010, which satisfies the alternating condition. Hence, the minimum number of flips required is 2. This demonstrates how the solution should change specific characters in the string to achieve the desired result. Now, consider the next input, 010. In this second example, the input string 010 is already alternating. Each character alternates between 0 and 1, and no two adjacent characters are the same. Therefore, no flips are needed, and the output is 0. In the third example, the input string is 1110. Here, we can flip the last character to turn the string into either 1010 or 0110, both of which are alternating. In this case, only one flip is needed, so the output is 1. These examples highlight how to approach the problem based on the input string's structure. Now, let's review the constraints and some important points to consider. The length of the string can be as large as 100,000, so the solution must be efficient enough to handle large inputs. Each character in the string is guaranteed to be either 0 or 1. Since the string is circular, the first and last characters are adjacent, which means the final alternating string must respect this circular property. Edge cases include strings of length 1 or 2, which are always alternating by default, as well as strings that are already alternating, requiring 0 flips. Additionally, some strings may require flipping nearly all characters, and in other cases, the circular nature of the string may significantly affect the result. A robust solution must account for all these scenarios while maintaining efficiency. To solve the problem of finding the minimum flips required to make a binary string alternating, we first need to understand the constraints and challenges. The string can be rotated, meaning any substring can potentially become the beginning of the string. Additionally, since the length of the string can be large, our solution must be efficient. One basic approach to consider is brute force. The intuition here is that an alternating binary string can only be one of two patterns, starting with 0 or starting with 1. For every possible rotation of the string, we can compare it with both of these patterns, calculate the mismatches, and record the minimum flips required. However, this approach involves generating all rotations of the string, which is computationally expensive. Specifically, for a string of length n, this would require O(n) squared time for rotations and an additional O(n) for each comparison, leading to an overall time complexity of O(n) cubed. For large inputs, this is not feasible, and we need a more efficient method. The brute force approach, while conceptually straightforward, is too slow due to its cubic complexity. A much more efficient method involves using a sliding window with pre-computed patterns. This approach eliminates the need to explicitly generate rotations. Instead, we treat the string as circular by appending it to itself, effectively creating an extended string. With this extended string, we can use a sliding window of size n to simulate rotations without actually moving characters. To implement this, we first pre-compute the two alternating patterns for a string of length 2n. These are the targets we will compare against. Then, as we slide the window over the extended string, we count mismatches between the window and each of these patterns, tracking the minimum flips required. This approach leverages modular arithmetic to handle the circular nature of the string, making the process highly efficient. The time complexity here is linear, O(n), as we avoid the overhead of explicit rotations and redundant computations. While dynamic programming can sometimes optimize problems involving rotations, it is less efficient in this context compared to the sliding window approach. Using dynamic programming, we might attempt to track the minimum flips needed for each rotation by storing intermediate results in a DP table. However, this method still requires explicitly iterating over all rotations, which results in a time complexity of O(n squared, or worse. This makes it less practical for large strings. On the other hand, the sliding window approach stands out as the most efficient solution. By avoiding explicit rotations and leveraging pre-computed alternating patterns, it reduces the computational overhead significantly. Constructing the patterns and processing the extended string both occur in linear time, making this approach highly scalable even for large input sizes. Its simplicity and efficiency make it the clear choice for solving this problem. The key insight that simplifies this problem is recognizing that we can treat the string as circular. By appending the string to itself and using modular arithmetic, we eliminate the need for explicit rotations, which are computationally expensive. Pre-computing the two alternating patterns further streamlines the solution, as we are always comparing against fixed targets. When comparing the different approaches, the brute force method is clearly impractical due to its O(n cubed) complexity. Dynamic programming, while an improvement, still falls short in terms of efficiency. The sliding window approach, with its linear time complexity, is optimal both in terms of speed and scalability. It avoids redundant computations and handles large inputs effectively. These observations and trade-offs highlight why the sliding window approach is the ideal strategy for solving this problem. To solve the problem of finding the minimum number of flips required to make a binary string alternating, we start by understanding the structure of alternating binary strings. These are strings that strictly alternate between zeros and ones, such as 010101 or 1001010. The key challenge lies in transforming the input string S into one of these alternating patterns with the fewest flips. Additionally, the string S can be rotated, meaning any prefix can be moved to the end, which introduces more potential configurations to evaluate. The algorithm begins by defining the two possible alternating patterns, pattern A, which starts with 0 and alternates, such as 010101, and pattern B, which starts with 1 and alternates, such as 1001010. The length of these patterns is determined by the length of the input string S. For example, if S is 1110, then pattern A would be 0101 and pattern B would be 1010. Next, to account for all possible rotations of S, we extend the string by concatenating it with itself, resulting in extended _s equals S plus S. This enables us to simulate any rotation by examining substrings of length n, the length of the original string, within the extended string. Finally, we use a sliding window of size n to compare these substrings with the two patterns, calculating the number of flips needed to match each pattern and tracking the minimum flips across all rotations. When comparing substrings in the sliding window, we calculate the number of mismatches for each pattern. For pattern A, we count how many characters in the current substring differ from the corresponding characters in pattern A. Similarly, we count mismatches for pattern B. The goal is to find the minimum number of flips required to match either pattern across all possible rotations. To implement this efficiently, we pre-compute the two patterns in a single pass, which takes O(n) time. During the sliding window comparison, we optimize the mismatch calculation using an incremental approach. As the window slides, we adjust the mismatch counts by removing the contribution of the character that leaves the window and adding the contribution of the character that enters. This avoids recalculating mismatches for the entire window each time it shifts, ensuring the process remains efficient with an O(n) runtime. The insights that drive this approach include the ability to simulate rotations through string concatenation, which eliminates the need for explicit rotations, and the realization that there are only two possible patterns to compare against, simplifying the problem. The sliding window technique reduces redundant computations, making the algorithm highly efficient and structured. To implement the solution, we use a combination of data structures and techniques. String concatenation is employed to simulate rotations efficiently by creating the extended string s plus s. The sliding window technique is used to calculate mismatches incrementally, ensuring that we don't recompute values unnecessarily as the window shifts. Additionally, counters are used to track the number of flips required for each pattern within the current window. This approach is both time-efficient and space-efficient. The overall time complexity of the algorithm is O(n). This includes O(n) for generating the two alternating patterns and another O(n) for the sliding window comparison. The space complexity is also O(n), as we store the extended string in the two patterns. It's crucial to handle edge cases. If the string s is already alternating, the number of flips is 0. If s contains only zeros or only ones, then transforming it to match either pattern will require flipping every single bit. For very short strings of length 1 or 2, rotations don't change the string, so these cases should be handled explicitly. These considerations ensure the algorithm remains robust across all inputs. The pseudocode breaks down the implementation step by step. First, we calculate the length of the string s and create the extended string s plus s. We then generate the two alternating patterns, pattern A and pattern B, based on the length of s. Next, we initialize mismatch counters for both patterns and calculate the mismatches for the first window of size n in the extended string. As we process the extended string, sliding the window one character at a time, we update the mismatch counters incrementally. When the window slides, we subtract the contribution of the character that exits the window and add the contribution of the new character that enters. This ensures the mismatch counts remain accurate without recomputing them from scratch. At each step, we update the minimum number of flips required. By the end, the algorithm returns the minimum flips, which represents the optimal solution. This approach leverages efficient data structures and techniques to handle all rotations, ensuring the solution is both elegant and performant. Here, we begin by defining the min-flips function, which takes a binary string s as input. The first step is to determine the length of the string, stored in n. Next, we create two possible alternating patterns, alt1 and alt2, that represent the two valid alternating binary sequences. Alt1 starts with 0, while alt2 starts with 1. Both patterns are generated to be twice the length of the input string to account for the sliding window approach we'll use later. Then, we extend the input string s by concatenating it with itself, resulting in s_extended. This allows us to simulate all possible rotations of the string without actually rotating it. We initialize a variable min_flips to positive infinity, as we aim to find the minimum number of flips required. Two counters, diff1 and diff2, are also initialized to 0, which will keep track of the differences between the extended string and the two alternating patterns during the sliding window process. The for loop begins, iterating through each character in the extended string up to 2*n. Within the loop, we compare the current character of s_extended to the corresponding characters in alt1 and alt2. If there's a mismatch, the respective difference counter is increment. This effectively tracks how many flips are needed to align the current window with each pattern. Now, as the loop continues, we handle the sliding window mechanics. Once the window size exceeds the original string length n, we start removing the influence of the character that's sliding out of the window. This is achieved by checking whether the character at position I, n in s_extended contributed to a mismatch with alt1 or alt2, and decrementing the respective difference counter if it did. Finally, for every index where the window size matches the input string's length, we calculate the minimum flips needed by comparing diff1, diff2, and the current value of min_flips. This ensures that we are always updating min_flips with the least number of flips required to make the binary string alternating for all possible rotations. Once the loop completes, we return the value of min_flips as the result, which represents the minimum number of flips needed to achieve the desired alternating binary pattern. Here, we start by defining the min_flips method, which takes the binary string s as input. The first step is to determine the length of the string, ken, which will help us handle rotations and comparisons later. To create reference patterns for alternating binary strings, we use two string builder objects, alt1 and alt2. The first pattern, alt1, represents an alternating sequence starting with 0, while the second pattern, alt2, starts with 1. We generate these patterns for twice the length of the string, as we'll be simulating the string rotation by extending the original string. Next, we extend the given string s by concatenating it with itself and store it in sExtended. This extended string allows us to efficiently simulate rotations without explicitly modifying the original string. Additionally, we initialize min flips to the maximum possible integer value, as this will keep track of the minimum number of flips needed. Finally, we declare two variables, diff1 and diff2, to measure how many characters differ between the extended string and the two alternating patterns during our sliding window traversal. To handle the sliding window logic, we iterate through the extended string using a loop. At each step, we compare the current character of sExtended with the corresponding characters in alt1 and alt2. If there is a mismatch, we increment the respective difference counters, diff1 or diff2. When the window size exceeds the original string length n, we shrink the window by checking the character that moves out of the window and decrementing the corresponding difference counters if there was a mismatch. This ensures that we are only considering the current window of size n. Once the window size reaches n, we calculate the minimum number of flips required for the current window by taking the smaller value between diff1 and diff2, and update min flips accordingly. After completing the traversal, the method returns the smallest number of flips needed to make the string alternating, ensuring that all rotations are considered. To solve this problem, we start by considering the two alternating patterns that the binary string may need to match. The first pattern, alt1, starts with 0 and alternates as 01010101. The second pattern, alt2, starts with 1 and alternates as 10101010. Since the binary string can be rotated, we simulate all possible rotations by extending the string. For the input s equals 1110, the extended version is s_extended equals 11101110. Next, we use a sliding window of size n equals 4, the length of the original string, to calculate the minimum number of flips needed. We initialize variables diff1 and diff2 to track mismatches against alt1 and alt2 respectively, and set min_flips to infinity. These initializations allow us to efficiently calculate the mismatches as we slide the window across the extended string. We start analyzing the windows. For the first window, 0:4, the substring s_extended, 0:4, is 1110. Comparing it with alt1, 0:4, equals 0101, there are mismatches at positions 0, 1, and 3, so diff1 equals 3. Comparing it with alt2, 0:4, equals 1010, there's a mismatch only at position 2, so diff2 equals 1. The minimum flips required for this window is min_flips equals min, inf, 3, 1, equals 1. Moving to the next window, 1:5, the substring s_extended, 1:5, is 1101. By adding the mismatch for the new position at index 4 and removing the mismatch from the old position at index 0, we update diff1 to 2 and diff2 to 2. The min_flips remains 1. Now for window 2:6, the substring is 1011. Comparing this with alt1 and alt2, we find diff1 equals 3 and diff2 equals 1. The min_flips stays at 1. Next, for window 3:7, the substring is 0111. Comparing against alt1, there are mismatches at all 4 positions, so diff1 equals 4. Against alt2, there are no mismatches, so diff2 equals 0. This gives us a new min_flips equals min, 1, 4, 0, equals 0. Since this is the lowest possible value, no further flips are needed. The output for this example is min_flips equals 0. Moving on to the second example, where the input string is s equals 100101, we start by generating the alternating patterns. Here, alt1 extends to 010101010101 and alt2 extends to 101010101010. The extended string becomes s_extended equals 100101101001. With the string length n equals 6, we initialize diff1 equals 0, diff2 equals 0, and min underscore flips equals infinity to begin the sliding window calculation. For the first window, 0:6, the substring is 100101. Comparing with alt1, there are mismatches at positions 0 and 5, so diff1 equals 2. Against alt2, there are mismatches at positions 1, 3, and 4, giving diff2 equals 4. The minimum flips for this window is min underscore flips equals min, inf, 2, 4, equals 2. For window 1:7, the substring is 001011. After adjusting the mismatches for the new position at index 6 and removing the old position at index 0, both diff1 and diff2 become 3. The min underscore flips remains 2. In window 2:8, the substring is 010110. Here, diff1 is updated to 2, and diff2 becomes 4. The min underscore flips stays at 2 as it is the smallest value so far. For window 3:9, the substring is 101100. Comparing against alt1 and alt2, both diff1 and diff2 are 3. The min underscore flips remains 2, as no smaller value is found. Thus, the output for this example is min underscore flips equals 2. Now, consider the third example where the input string is s equals 0000. As before, we generate the alternating patterns. Alt1 is 01010101 and alt2 is 10101010. Extending the input string gives s underscore extended equals 00000000. With n equals 4, we initialize diff1 equals 0, diff2 equals 0, and min underscore flips equals infinity. For the first window, 0:4, the substring s underscore extended, 0:4, is 0000. Comparing it with alt1, 0:4, equals 0101 results in mismatches at positions 0 and 2, so diff1 equals 2. Against alt2, 0:4, equals 1010, there are mismatches at positions 1 and 3, giving diff2 equals 2. The minimum flips for this window is min underscore flips equals min, inf, 2, 2, equals 2. For window 1:5, the substring is also 0000. Since the mismatches remain the same, diff1 equals 2 and diff2 equals 2, so min underscore flips stays at 2. Thus, the output for this example is min underscore flips equals 2. This concludes the explanation of how to find the minimum number of flips for these examples. In analyzing the time complexity of our solution, let's start by breaking it into its core steps. First, we generate two alternating patterns, alt1 and alt2, which represent the two possible alternating binary strings. To do this, we iterate over a range of size 2*n and concatenate either 0 or 1 as appropriate. Since this loop runs 2*n times, the time complexity for generating these patterns is O(2*n), which simplifies to O(n). Next, we extend the input string s by concatenating it with itself, creating the string s underscore extended. Since the length of the input string is n, this operation also requires O(n) time. These two steps lay the groundwork for the sliding window approach, but their overall contribution remains linear in nature. Now, we move to the core of the algorithm, the sliding window comparison. Here, we iterate through the extended string s underscore extended, which has a size of 2*n, and compare it against the alternating patterns alt1 and alt2. This process is completed in a single pass, making its time complexity O(2*n), which simplifies to O(n). For each character in s underscore extended, we perform constant time comparisons to the corresponding characters in alt1 and alt2, which means these comparisons contribute O(1) time per step. Additionally, the sliding window logic involves adjusting the difference counts, such as diff1 and diff2, which are updated with constant time operations as well. After processing each window, we calculate the minimum flips required by comparing min underscore flips, diff1, and diff2, another constant time operation. Combining all these steps, the dominant factor in the time complexity remains the sliding window logic, resulting in an overall time complexity of O(n). Let's now focus on the space complexity. The algorithm requires memory for three main components. First, we have the alternating patterns alt1 and alt2, each of size 2*n. This results in a space requirement of O(2*n), which simplifies to O(n). Similarly, the extended string s underscore extended is also of size 2*n, contributing another O(n) to the space complexity. Finally, the algorithm relies on a handful of integer variables such as diff1, diff2, min_flips, and the loop index, all of which use constant space or O(1). Since the memory usage is dominated by the storage of alt1, alt2, and s_extended, the total space complexity of the algorithm is O(n). To better understand the efficiency of this approach, let's compare it to a brute force method. In a naive solution, we would simulate every possible rotation of the string S and calculate the flips required to match the alternating patterns. For each rotation, this involves O(n) comparisons, and since there are n rotations to check, the total time complexity becomes O(n squared). In contrast, the optimized sliding window approach avoids simulating these rotations altogether. By extending the string and processing it with a sliding window, we calculate the flips in a single pass. This reduces the time complexity from O(n squared to O(n), representing a significant improvement in efficiency. Finally, let's summarize the best, average, and worst-case performance of the algorithm. In the best case, the algorithm processes the input in O(n) time, as the sliding window ensures every character in s_extended is processed exactly once. The same logic applies to the average case, where the efficiency remains O(n), regardless of the binary string structure. Even in the worst case, where the binary string could be highly irregular, the sliding window approach ensures that no unnecessary computations are performed, maintaining O(n) time complexity. Mathematically, the algorithm processes each character in s_extended exactly once, performing constant time operations for updates and comparisons. Since s_extended has a length of 2*n, the total work amounts to 2*n constant time operations, leading to an O(n) time complexity. The space complexity, dominated by the strings alt1, alt2, and s_extended, is also O(n). When tackling this problem, there are a few common mistakes to watch out for. First, misunderstanding the two possible alternating patterns is a frequent issue. Remember, the string can alternate starting with either 0 as in 010101, or 1 as in 1001010. Failing to check both patterns can lead to incorrect results, so always calculate the number of flips required for each and take the minimum. Another pitfall is overlooking the fact that the string can be infinitely rotated. Some solutions assume a fixed starting point, which is incorrect. To handle this, you can simulate all possible rotations by concatenating the string with itself. Lastly, using a brute force method to test every rotation and count flips results in a time complexity of O(n squared, which is impractical for large inputs. Instead, you should adopt a sliding window approach to achieve an efficient O(n) solution. Another mistake to avoid is incorrectly counting flips. Some solutions mistakenly calculate flips for the entire doubled string instead of focusing on the sliding window of size n, which represents the original string's length. To fix this, ensure your logic only accounts for flips within the sliding window during rotations. Additionally, boundary cases are often neglected, such as strings of length 1 or those that are already alternating. These cases can cause unexpected errors or unnecessary computations if not handled explicitly. Always include checks for these edge cases to ensure the robustness of your solution. To succeed in interviews, it's crucial to grasp the key insights of this problem. Fundamentally, it boils down to comparing the string against two alternating patterns, 0101 and 1010, while accounting for all possible rotations. Using a sliding window technique on the doubled string allows you to efficiently simulate these rotations with a time complexity of O(n). Maintaining a running count of mismatches within the sliding window is essential to optimize this approach. Beyond this specific problem, recognizing and handling alternating patterns is a valuable skill that often appears in string problems. Finally, interviewers frequently test solutions with edge cases like very short strings, or strings composed entirely of zeros or ones, so being prepared for these scenarios is vital. If you're looking to deepen your understanding, consider exploring related problems on LeetCode. Problem 926, Flip string to monotone increasing, involves a similar concept of flipping bits to achieve a specific pattern, but focuses on monotonic sequences. Problem 1247, minimum swaps to make strings equal, also deals with minimizing transformations to meet a target pattern, though it uses swaps instead of flips. Problem 1754, largest merge of two strings, emphasizes constructing patterns through string manipulation, while problem 424, longest repeating character replacement, applies a sliding window technique to optimize string transformations. Studying these problems will broaden your perspective on how these techniques can be applied. There are multiple approaches to solving this problem, each with its trade-offs. A brute force method involves checking all possible rotations and calculating flip counts for each, but this approach is inefficient with a complexity of n squared. A more advanced option is to use prefix sums, where you pre-compute mismatches for both patterns and leverage these sums to quickly calculate flips for each rotation. This achieves n time complexity but requires additional pre-processing. The optimal approach is the sliding window method, where you extend the string by concatenation and use the window to maintain mismatch counts efficiently. This method is both time and space efficient, with n and O1 complexities respectively, though it requires careful handling of rotations to avoid errors. Great job reaching the end of this walkthrough. We've explored how to efficiently solve the problem by leveraging sliding window and modular arithmetic. Remember, mastering these techniques will help you with similar pattern-based string problems. Thank you for watching, and don't forget to like, share, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!